In the previous lessons, we've been talking about similar triangles and using similarity to find unknown side lengths. We're going to consider these right-angled triangles in the picture here. So we're looking at triangle ABC, which is the big outer triangle, and then DEC, which is a slightly smaller version, and EFC and GHC. Why are those four triangles all similar to each other? Well, right away I'm seeing that all of them include a 90-degree angle in the bottom corner. They also all share angle C. That is common to them. So that angle would all be the same for all three triangles. So by default, by angle, we know that those triangles have a similar shape to one another. So make sure you include the reasons so we know that it's similar by angle similarity. All right, we're going to complete the table here. We want to, for each triangle, list the length or state the length of the vertical side, which when we think of lines on the Cartesian plane, the vertical ones would be called the rise. So for GHC, so the small triangle in the bottom corner here, the rise looks like it's 1 centimeter because it's marked as being 1 centimeter. The length of the run is 3 centimeters. So remember, run is your horizontal length. And then the ratio of rise compared to run would be 1 compared to 3, 1/3. All right, so we want to do the same thing for triangle EFC. So that's a slightly bigger triangle. So the rise is clearly 1.5 centimeters. The run isn't marked here, but we can figure that out. We know these are similar triangles, so we're working with a scale factor to go from one to the next. Corresponding sides have to be a scale factor apart. So it looks like we're multiplying 1 by 1.5 to get 1.5. So that means we're going to multiply 3 by 1.5. And we get our answer for that one to be 4.5. So our ratio of rise to run is what I was trying to say is 1.5 over 4.5. And then we want to write that in better terms, because normally you wouldn't include decimals in fractions. Like, that's just weird. So I'm going to multiply both of those by 10, first of all, to make that 15 over 45, and then 15 can divide by 15, and 45 can divide by 15 3 times. So that's going to equal a 1/3. So the ratio of rise over run is 1/3. That should make sense because this is a constant slope that we are looking at. The slope from C to G would be the same as the slope from C to E. So knowing what we know about slopes, this should make sense. And similarly, you can fill in DEC and triangle ABC's information. So when you check your work, just make sure you have the same measurements that I have here, and your ratio of rise compared to run is 1 to 3, regardless of which triangle we're working with. All right, so let's move forward with this. Any scale factor can be factored out and reduced, making a ratio of rise to run equivalent for all similar triangles. So what I'm trying to say there is if you look at the red one here, we know that the scale factor was 1.5. So really, I could factor out 1.5 on the top, 1.5 times 1, and 1.5 times the 3 is really how we're getting the 1/3. The 1.5s divide out to be 1, and you end up with your 1/3 there. Same with the second one. To go from the 1 to the 2, we multiplied by 2. So 2 really is 2 times the 1, and the 6 really was the 2 times the 3. The 2's divide out. 2 divided by 2 is 1, leaving you with a 1/3. And similarly for the last one. All right, so we need to talk about this thing called slope angle. So we've talked about slope here. The slope angle is that angle C in our diagram. So this angle C, this angle here, is called the slope angle. It is the angle across from or directly opposite to the rise and right beside or adjacent to the run. Slope angle. So it is the angle that's always across from your rise and directly beside your run. The 1 is the side we say is opposite angle C, and the 3 centimeters here, so the 1 centimeter here, 3 centimeters here is the side adjacent to angle C. So let's just write in about the slope angle here. So my statement here is just that it's the angle formed in a right angled triangle. It's the angle across from or opposite to the rise and adjacent or beside, adjacent to the run. So if I look at this angle C here, grab my tool to write, this angle C, you'll notice this funny looking symbol here. This is the Greek letter theta. So I'm just going to write some things in here. The unknown angle can be marked with theta. Now it's kind of like X in algebra. It's just a symbol. It's a Greek letter of the Greek alphabet. And the reason we use the Greek letter is because the Greek history has been given credit for creating trigonometry. So this is a Greek letter. Okay, so we often use Greek letters for unknown angles. Theta is the most common one, but sometimes we use alpha or beta or gamma, different letters that we use. When I got to university, sometimes I used Chi and Psi, which I can't remember what it looks like right off the top of my head, but we use different ones in university as well. So the side across from it, it is the rise in the position that we've drawn it, but when we start twisting these triangles around, we're going to actually call that the opposite, because it is opposite to that angle that we are interested in knowing. And instead of actually writing out the word opposite, we just write OPP as short for opposite. That tends to be the short form we use. And then the side next to it is called the adjacent side. And of course we called it the run as well. And again, ADJ is a short form for adjacent. It's also the run when it's looking like a horizontal line. All right, now this brings us to something called the tan ratio or the tangent ratio. Tangent is the full form of it, but we often call it just tan. And if you look on your scientific calculator, you'll notice there is a button marked tan. It is short for the word tangent. So it is the tan ratio. Tangent ratio always has to be followed by an angle. You never leave your angle or your tan hanging. You always have to have an angle after it. So sometimes we just put in the theta. So the tangent ratio of angle theta would equal the opposite side, the side length opposite to it, divided by the length of the side that's adjacent to it. So that's what the tan ratio is defined as. So all of our triangles above had the tan of angle C equaling 1/3. Now the cool thing about that is we're going to find out how to actually solve for the measure of angle C, how many degrees it is, without having to use a protractor to measure it. The last thing I want to mark on this diagram before we go to the next part is the fact that you already know the side across from your 90 degrees is always called your hypotenuse. And that is true for every single triangle possible that has a right angle. If it doesn't have a right angle, it does not have a hypotenuse. You cannot call the longest side of a triangle a hypotenuse unless you have a right angle across from it. So your hypotenuse is always across from your 90-degree angle. Your side that's opposite is always opposite to your angle that you are either trying to find or that you know. It's called your angle of reference. So what I have marked here for my theta, this angle is the angle of reference. The angle of reference. And your 90 degrees will never be your angle of reference. Never the 90 degrees. Because you already know that one. You already know it's 90 degrees, and the side across from it cannot be called the opposite side. It has to be the hypotenuse. So never use the 90-degree angle as your angle of reference. Okay, so never the 90-degree angle. All right, so now let's actually work with this.